Hello students, I hope that you are good, well and fine. So, what we discussed or what we saw was we recalled something. We saw a relation definition, we saw a relation representation and the total number of possible relations from set A to B. Okay, and now what we will be seeing? We will be mainly covering types of relations. Types of relations, you will see types of relation: reflexive, symmetric, reflexive, symmetric and transitive. Okay, transitive. Okay, in today's session what we will be covering this. Okay, so let us see, so what do we mean by what reflexive first. So before jumping to the main types, we will see these also. So empty relation is defined from A to A if my relation is defined from where to where? A to A. If A to A, so if relation R is A to A, this what this means is the R must be subset of A cross A. Okay, is called what? Empty relation if no elements of A is related to any element of A. Okay, so in other words, if you try to see what you can say, for example, say A is what? A is just this element, then A cross A will be what? 1 comma 1, that's it. Yes, so your R, if you try to define R, what your R will be, you can say that R is just empty set, because R is what? As you remember, R must be subset of A cross A. Yes, it is. And what we are saying that in this relation or in this set, we have no elements related to each other. Yes, so what we can say is quite simple. If R is empty, sorry, if no elements of A related to any element of A, then we say that R is equals to empty relation. Okay, R is equals to empty relation or phi relation. So R is a, say, A comma B such that A belongs to A and B belongs to B and B belongs to A also. The relation is defined like this. How we are defining A? That A not equals to B. Okay, so for example, this, if A is just 1 and A cross A is this, then write all those collection of ordered pairs such that which hold this thing. As you can see, in A cross A we have only one element, and from this we know that 1 is equals to 1. So this means we have no other element which satisfies this. This means R must be what? Just empty set or phi set, and this is what? Subset of A cross A. So by definition it is what? Empty relation. Okay, I hope that it is clear to you. And the main important thing over here is that empty relation is defined from where to where? A to A itself. Okay, the same thing goes for universal relation. Universal relation is what? That R is A to A. R is my relation, and from where to where? A set to A set itself. Then if the relation this set is equals to the whole set A cross A, then I will say that my relation is what? Universal relation. For example, if you manipulate this, if you say that your relation is what? You are defining your relation like this, that collection of all ordered pairs such that A belongs to A, B belongs to B. Okay, just this. A belongs to A, B belongs to B. So if you try to write it down, what you will get is this set, and this set is what? This set is equals to this. So this means by definition, what is your universal set? This. So I will call this relation R as my universal set. Okay. I hope that it is also clear to you. Very simple, very straightforward definitions. The main thing is just that in both of the relations, my relation is from where to where? A to A itself. Okay, I hope that it is clear. Now, the main definitions, the reflexive, symmetric, and transitive. So, when do we say that a given relation is reflexive? So, A comma A must belongs to the given relation for every A belongs to the set A. Okay, every A belongs to the set A. So this means then we only can say that my relation is what? Reflexive. Okay, you will see examples. First of all, let us see the definitions. Now symmetric, if this pair belongs to the relation R, then this pair also belongs to the relation R. What this means? This means that if this pair belongs to the relation R, which means the first element is A1 and second element is A2, then if you interchange the first and the second element like this, that A2 now becomes the first element and A1 becomes the second element, then this whole pair must also be in the set R. If this happens, then we say that my relation is what? Symmetric. Okay. Okay. Now what about transitive? Transitive is like to share. For example, before example, let us see the definition. So whenever A1, A2 belongs to the relation R, and there is another pair which starts from A2 as you can see and end up with another element, say A3, then this A1 and A3 pair, as you can see over here, this A1 and A3 pair belongs to the R, then what you can say? You can say that my relation is transitive. And if my relation is reflexive, symmetric as well as transitive, then I can say that my relation is an equivalence relation. Equivalence relation means that it satisfies reflexivity, symmetricity and transitivity. Okay, I hope that it is clear. Let us move to next. From an example, we will be understood. Okay, so now let T be set of all triangles in a plane. Okay, so T is what set? T is a what? Collection of all triangles. All triangles. Okay. Now R a relation in T given by, so R is what must be subset of T cross T. As you can see, R a relation in T. This means T to T. Now R defined by collection of all pairs T1 comma T2 such that, or we can say collection of all pairs T1 comma T2 such that T1 is congruent to T2. What this means? This word means same in shape and size. Okay. This means more clearly, if you have 5 rupee coin, then and another person has 5 rupee coin, we know that those 5 rupee coins will be same. Yes, in shape and size. If you try to overlap them, they will cover each other. Yes, if you put say this is one the person having what? This coin, and another person having this coin. I am naming them as 1 and 2. Then if you try to put this second coin over the first, the second coin will completely completely overshadow the first coin or completely cover the first coin. If you try to do the same thing with the first coin, then your first coin will completely hide the second coin. So this means that they must be what? Same. Yes, they must be same. That's why they can easily uh, hide each other. So congruent means same in shape and size. Okay, I hope that it is clear. Now let us prove that it is reflexive. So reflexive means a comma a must belongs to the relation R for every a belongs to what set? A. Yes, okay. So uh, for here we want to show that T1 comma T1 must belongs to the relation R for every or you can say for every T1 belongs to set of what? Set of all or the collection of all triangles which is T. Okay, so this means this. Okay, we know that any triangle T1 is congruent to itself. Yes, this means any triangle T1 is same as itself, same in size and same in shape. Yes, so this means T1 is congruent to T2. So this means T1 is congruent to T2. Sorry, T1 is congruent to T1 itself. This is what? Congruency symbol. This is what? Congruency symbol. Okay. So from this what I can say that T1 comma T1 belongs to relation R for every T1 belongs to the set T. So it is reflexive. Yes. Now what about symmetric? Okay. So now symmetric. So symmetric definition says whenever we have a pair A comma B in relation R, then B comma A also belongs to the relation R. This must happen. Okay. So now to show that if T1 comma T2 belongs to the relation R, this implies T2 comma T1 also belongs to the relation R. Okay, let us try to show it. So given information is what? This, that T1 comma T2 belongs to the relation R. This means that T1 and T2 are same in shape and size. Okay, this means T2 is also same in shape and size. Yes, T2 is also same in shape and size like T1. Yes, this means this means T2 is congruent to T1. Yes, this thing means T1 is congruent to T2, and we have arrived to this. This will imply that T2 comma T1 belongs to the relation R. Yes, so we have showed that whenever this happens, we will have this. Yes, so this means it is symmetric also. Okay, now what about a transitive relation? So recall the definition. So what definition says is very clear that whenever A comma B belongs to relation R and B comma C belongs to relation R, then we must have A comma C belongs to relation R. If this happens, then we say that our relation is transitive. Okay. Now to show that T1 comma T2 belongs to R and T2 comma T3 belongs to R, this means T1 comma T3 also belongs to R. Okay. So given thing is what? This, that T1 comma T2 belongs to R. This implies that T1 is congruent to T2. Yes. Okay. T2 comma T3 belongs to R. This means that T2 is congruent to what? T3. Okay. This means what? Okay. So this means what? That T1 is same as T2. Yes. And from this what we can say is T2 is same as T3. Yes. And from both of these statements what we can say is T1 is same as T3. This means T1 is congruent to T3. This means what? T1 comma T3 belongs to the relation R. So it is transitive also. Yes, it is what? Transitive also. Okay, quite simple. So this is what? So this is what? An equivalence relation. When my relation is symmetric, transitive and reflexive, then my relation will be an equivalence relation. Okay, I hope that it is clear. Okay, now another example. More you do examples, you will get the concept clearer. Okay. Okay, now this. Show that the relation R in the set, so my relation is from where to where? This set to this set itself. Okay, so R must be subset of what? 1 2 3 cross product with 1 2 3, or you can say the Cartesian product. Okay, the Cartesian product will be what? If you try to what evaluate it, how many elements you will get in your Cartesian product? 9, because 9 is 3 times 3, and the total number of element in this set is 3. The total number of elements in this set 3, so this means 3 times 3 times you will get as 9, and 9 will be your number of elements in the Cartesian product. Okay. Okay, your R is given like this. Okay, is your R reflexive? As you can see, let us see. So for reflexivity, what we need, that A comma A must belongs to the set R for every A belongs to the set A. Okay. Okay, so as you can see here, R is from what set? This set to this set. Yes. Okay, and in this case R is from where to where? A to say A. Okay. Okay, now what? Now this means A comma A must belongs to R for every A belongs to which set? 1 2 3. Okay, so this means 1 comma 1, 2 comma 2 and 3 comma 3 must belongs to R. Is this happening? As you can see, 1 comma 1, 2 comma 2, 3 comma 3 belongs to R. So yes, it is reflexive. By definition it is reflexive. Okay, no issue in that. What about symmetric and transitivity? So for symmetricity, if you recall the definition, okay, for symmetric, let me remove it. Okay, so for symmetric, for symmetricity, it is quite clear. So symmetric. Now, whenever we have what? A comma B. Whenever we have A comma B, whenever we have A comma B in in a given relation R, then B comma A must be in the relation R. If this is happening, then we can say that our relation is what? Symmetric. So let us see. So 1 comma belongs 1 comma 1 belongs to R. Okay. If you interchange what you will get? The same element. If you interchange these elements, you will get the same element. If you interchange these elements, you will get the same elements. Okay. Now this 1 comma 2 belongs to the relation R, but as you can see, if you interchange the positions, what you will get as this 2 comma 1. Does this pair belongs to relation R? As you can see, no. So this means this does not belongs to the relation R. So this means the given relation not follows the definition of symmetric. So this means not symmetric. Okay. Now what about transitivity? So recall the definition for transitivity. So very a simple definition. So what it says? It says whenever, so for transitivity, okay, for transitive, whenever A comma V belongs to the relation R and B comma C belongs to the relation R, then A comma C must also be present in the relation R. If this is happening, then we can say that my relation is transitive. So if you try to see what pairs, these two pairs 1 comma 2 belongs to R and 2 comma 3 belongs to R, but as you can see A and this C elements, so 1 comma C, does this pair belongs to the relation R? As you can see, no. So this means this 1 comma 3 does not belongs to the relation R. It does not belongs to the relation R. So what it means? It means that my given relation is not transitive also. Okay. So simply what we did, just we contradict the definition for symmetric and transitive to show that it is neither symmetric and transitive. Okay, and it is reflexive. I hope that you got the proof. Let us move to next. Now in this example, what it says is, it is saying that we need to show the given relation R from where to where? The set of integers. So R must be what? Z cross Z subset. Okay. The relation given by this collection of all AB such that 2 divides A minus B. Okay. 2 divides A minus B, and this thing is what? In other words, what you can write it as like this: collection of AB such that A minus B is equals to 2 times K, where K belongs to some integer. Yes, K belongs to some integer. Okay. Now what? Okay, so we need to show that this relation is an equivalence relation. So first of all, what we need to show, that it is reflexive. So definition for reflexive is what? A comma A must belongs to the relation R for every A belongs to the set A. So here in this case, my set A is what? The set of integer. Okay. So this means I have to show, so to show A comma A belongs to the relation R for every A belongs to the set of integers. Okay, we know what we know, that A minus A is equals to 0. Yes, A minus A is equals to 0, and this 0 is what? Is an integer. Yes, it is an integer, and this integer is what? Divisible by 2, and it is divisible by 2. Yes, or in other words, 0 is equals to 2 times 0. Yes, so this means this is what form? Like this: A minus B is equals to 2 times K. K belongs to integer set. Yes, So we showed that a comma a also belongs to the set, sorry, the relation R. Okay, I hope that it is clear. For every a belongs to the set of integer. Okay, I hope that it is clear. So it is reflexive. Now what about symmetric? Now for symmetric definition, if you recall, whenever so whenever so whenever we have a comma b pair in the relation R, then we must also have b comma a in R. If this is happening, then we say that our relation is symmetric. So to show, in this case, to show, what we need to show is that a comma b belongs to the relation R, imply b comma a belongs to the relation R. Okay, so quite simple. So given thing is a comma b belongs to the relation R. This means a minus b is equals to 2k for some k belongs to the set of integer. Yes, as you can see over here, a minus b. Okay, from this what you can say, if you multiply minus side minus 1 to both side, what you will get is b minus a is equals to minus 2k, and this is equals to just nothing but 2 of minus k, and minus k is just nothing, some integer. So minus k is some integer. Yes, so b minus a is equals to also uh, what it is also divisible by 2. So this means 2 divides b minus a. This means what, b comma a belongs to relation R. Okay, so it is symmetric also. Okay, now what about transitive? So transitive definition means whenever a comma b belongs to relation R and b comma c belongs to relation R, then a comma c belongs to relation R, we say that my relation is what, transitive. So to show, so in order to show, what we know is, so given information is what, a comma b belongs to relation R and b comma c belongs to relation R. From this what I can say is that a minus b is equals to what, some 2k. Okay, and from here what I can say, b minus c is equals to, say if this is k1, then 2k2, and k1 and k2 are some integers, Okay, now add both of the equation, the equation 1 and the equation 2. Add 1 and 2. This means what you will get is a minus v is equals to 2 k1 plus k2. Yes, and this k1 plus k2 is what, some integer. Yes, so this means what, this means that 2 divides a minus c. This means a comma c belongs to relation R. A comma c belongs to relation R. Yes, so it is transitive also. So we have showed that it is symmetric, it is reflexive, and it is transitive. So what this means? This means that my given relation will be what? An equivalence relation. Okay, I hope that you understood everything. So that's it for now. We will meet soon in the next lectures. Thank you.